I have to thank the organizers for the invitation to be here at Alex's 70th birthday celebration. So let me say a few words about Alex. I've known Alex for more than about 30 years, and our collaboration goes back to 25 years. And Alex has a very special attitude towards doing mathematics. So let me illustrate this with a little anecdote. So when I first started working with Alex, I had a certain problem about meromorphic functions. And I had a proof in the case of rational functions. So I ran my ideas by several people. And the typical answer was, oh, if it works for rational functions, why should it work for meromorphic functions? So when I ran this idea by Alex, he said, oh, it works for rational functions, so it must work for meromorphic functions. This is how we started collaborating with each other. It is actually very easy to work with Alex, but you have to agree to his terms. And the deal is the following. Alex, if he wants to collaborate on a project, will devote all available free time on the project. But the condition then is also that you do the same thing in turn. He will get very mad at you if you don't reply his emails, within 24 hours. So what I will talk about today actually goes back to some questions that Alex posed. So I will talk about Lamé functions and special elliptic integrals. When I was preparing my talk, my plans for this talk evolved a little bit. There will actually be no Lamé functions today. And actually, I'm not sure whether special elliptic integrals will even appear. So now you can wonder, what is left if remove all these terms. As it happens, these objects somehow lurk in the background of what I will present to you today, but somehow implicitly. And I won't have time actually to make this very explicit. As I mentioned, what I will talk to you today about is based on a question that Alex posed. Actually, a year ago, he sent me some unpublished notes with some historical remarks. And, I didn't reply to his email. But then more recently, he sent this again, and I took this as a hint that finally I should maybe think about this a little bit. And let me start my story with going a little bit into the history, which I think is an interesting story just by itself. And the problem is the following. Can you see the bottom here from the back? Okay. So so the problem that I want to start with is a problem actually of rational approximation theory. So you look at the function e to the minus x on the positive real line, and you want to approximate it by a rational function of degree n. Right, so you're interested in this kind of error that you make in this approximation onto the positive real line, and you want to infirmize this over all rational functions, let's say of degree. This is rational functions. Degree less equal n, right? And this is some of the error term in this approximation problem. And this was studied in the 60s, and it actually turns out that you get an exponential decay for this error term. So as n tends to infinity, one observed numerically that the rate is something like 1/9 to the n. So this was observed by computing this somewhat explicitly for the first few n, and then somebody conjectured that this 1/9 is the right rate, and this became known as the 1/9 conjecture. But in the early 80s, powerful numerical methods and powerful computers became available, and it was Nick Trefethen who actually computed this with higher accuracy, and he actually found. So let me write this down. So Nick Trefethen. He actually found that this numerics is actually not quite accurate. This was in 1981. this numerics is not quite accurate, but one should rather replace this constant 9 with 9.28903.n. Okay. So he had, at the time, he wasn't able to prove this, but he found this numerically. There's some funny anecdotes about this that you can find on the internet. For example, once he found this, he wrote a telegram to a colleague just with this number and a question mark behind. Right. So I think isn't it pi squared more or less? No, we will see what it is. So I think this somehow became a famous problem in numerical approximation to establish this asymptotics accurately. And this was then later in the late 80s solved by, I think, a team of Russian mathematicians. So this was proved by Bonk and Rachmanov. In 1989. Alex, in your note, you say 1987. What is correct?
Huh? What?
In your notes that I'm referring, you have the reference 1987, but I somehow found 1989.
Well, maybe it's an English translation of 1989.
All right. So anyways, around the time of the late 80s, there was a proof, and they actually found the precise constant here. So they showed that En is asymptotic to, let me call it x naught to the n, where this x naught is the solution of a somewhat weird looking equation. Solution of, let me write down the equation. This is actually also in Alex's notes. And from 1 to infinity, then you have certain coefficients. And the coefficients are for each n, of course. And they're somehow computed from the divisors of n. So you take a divisor of n, you raise it to the power minus 1 to the d times d. You sum this all up over all the divisors. You take the absolute value. You have x to the n. And you put this equal to 1 over 8. And this is this x naught that we're looking for. So numerically, this x naught is roughly, well, it's this number here. 1.28 and so on. Right, for the purpose of my talk, actually, let me actually look at the reciprocal. Namely, this is 0.1076 and so on. This equation is a little bit mysterious. But Guancha and Rachmanov, they realized actually that this constant comes somehow from the theory of elliptic functions. So this expression is not any kind of random expression. It is really related to the theory of modular forms, actually, how we will what we will see later today. The interesting thing is that it was not the first time that this funny constant actually appeared. Namely, it appeared much earlier. Namely, there's a book by Alphin, I don't know how to pronounce it, French mathematician, and he wrote a 3-volume Traité de fonctions elliptiques. And in the first volume on, I actually looked it up, volume 1, this is it's a massive work in 3 volumes. So in the first volume, on page 287, and later also on page 427, he has a funny equation that looks quite different from this equation. So again, some kind of a power series with certain coefficients, minus x to the n times n plus 1 divided by 2. If you set this equal to 0, then you can show that there's a unique positive root. And guess what this root is? Is x equal to this number. So he found this somehow by studying zeros of derivatives of theta functions, right? I mean, the experts somehow recognize here that this looks like a Q series differentiated twice. So this is actually to do with a second derivative of the theta function. And for some reason, I mean, you don't see it in his book. He really is obsessed with this constant and computes it actually to relatively high accuracy. It turns out that this funny constant appeared even earlier. So this was in 1886. Okay. This was in 1886 when this was published. But the funny constant that we see here appeared earlier. It's not here. Actually, it appeared much earlier, namely in work by Euler from 1744. Euler, 1744. So Euler was interested in classifying elastic curves. So what is an elastic curve? Think of a curtain rod or something. So you can bend a curtain rod, right? And depending on, let's say, how long the curtain rod is, how flexible the curtain rod is, what is the initial position where you take the ends, it will take a certain form, right? And well, if you have a very long curtain rod, it can actually happen that this form closes to a closed curve. And Euler found that there are two such closed curves. Well, of course, the circle, right? But then there's another closed curve that looks like a figure 8. Okay. And Euler classified all these curves, not necessarily closed by a parameter. And he found that in order to get this case here, the parameter, let me call it kappa for the purpose of my talk, has to do with a certain equation, namely 2e of kappa minus big K of kappa equal to 0. This is a modern notation where these e's and kappas here are the so-called complete elliptic integrals of the first and the second kind. Write it down here for the record. So the complete elliptic integral of the first kind, so capital K of little kappa, is equal, I mean, you've all seen this, equal from 0 to 2 pi, pi half of dt square root 1 minus kappa squared times tau. Yeah, so this is the complete integral of the first type. And there's the integral of the second type, where you have the same expression, but not in the denominator, but rather in the numerator. Okay. So Euler computed this kappa numerically. Actually, he made a little bit of a mistake. I haven't looked at Euler's original paper, but I saw it some translation with comments. So I think the original paper was written in Latin. So there was some later translation, English translation with comments. And they said that Euler made a numerical mistake when he computed this constant here. Well, what has this constant to do with our x naught that I introduced earlier? Well, I mean, for this, you have to use some kind of standard facts in the theory of elliptic functions. Namely, if you know a little bit about this, then you know that somehow these elliptic integrals are related to doubly periodic functions where one of the periods is given by this expression. The omega 1 here is this elliptic integral, the first kind. And the second period is given by a similar expression where you take, instead of kappa, the so-called complementary module. So they are related by, well, the module kappa squared plus this complementary module. You take the square and sum them up, and they equal to 1. And well, I mean, what is often interesting is this period ratio. Actually, let me change notation so that this is consistent with what I will say later. But from this, you compute this ratio tau. And now how do we get our x naught here? Well, you take the q of it. So, I mean, for those who know a little bit about elliptic functions, you know that this q here is a very important quantity. And if you feed in this kappa here, well, then you get again. So, okay. So all these numbers are the same. And you see, I mean, they somehow are obtained by solving quite different equations, right? So it's not actually hard to see that this equation here actually has exactly one solution in the interval from 0 to 1. Namely, well, if you just plot what these expressions are, right? I mean, if you plug in kappa equal to 0, then you see that this integral of the first type is pi half, and one can easily show that it actually tends to infinity. Okay, and for the E2, actually, it tends, you know, since you have the factor 2 here, it starts by at pi is monotonically decreasing, and I think it decreases to something like 2 if I compute it right. Right, so it's easy to see that there will be some kind of a root at this kappa here. Well, picture's not very good. So this is rather easy to see. So what is the question now? Well, I mean, the question is, how do you explain this kind of seeming coincidences? And how do you study actually the roots of expressions like this? This relates to the theory of modular forms and, you know, periods of elliptic. This is what I want to explain in my talk. For this, I have to give you a quick crash course on the theory of elliptic functions in the Weierstrass formulation. This will be familiar for many of you, for Alex certainly. But let me just write down some formulas. Hopefully I've seen in one form or the other. So let me set the stage here. So we want to look at the Weierstrass theory. Elliptic functions. So we start with the rank 2 lattice in the complex plane. So we have these two generators, complex numbers that are non-zero and linearly independent over R. So they generate a lattice. Okay. That is. And associated to this fixed lattice are these elliptic functions that Weierstrass introduced. So the most prominent one of them is the Weierstrass P function. Right. Usually, if the lattice is fixed, when someone drops the gamma, the lattice from the notation, but sometimes it is important if someone mention it, in particular if several lattices are involved. And sometimes, actually, you want to also keep track of the lattice generators. Right. In this case, you can consider the P function as a function of 3 variables, right? And by definition, I mean, this is given by a series where you have double poles at all the lattice generators. You have some sum where you run through all the lattice elements, and you have a term that creates a pole of order 2. Right, but if you just look at this series, it will not converge. So it was Weierstrass's insight to add a term here that makes the expression convergent, but somehow still preserves the double periodicity. Right? That's the most crucial property of the P function. It is doubly periodic with respect to this given lattice. Yeah, let me keep this. Right, so what are the most important properties? As I said, the P function is periodic, right? And it's, of course, just enough to require this periodicity property for the lattice generators. Another important property is, if I consider this as a function of 3 variables, that it's actually homogeneous of degree -2, right? In other words, if I multiply all the 3 arguments by some t, non-zero, then it comes out as t to the -2. T here is 0. You can see this immediately from inspection here, right? If you scale everything by t, I mean, then you will get power. So this is homogeneous. -2, right? And then, I mean, another important property is that you've all seen the Weierstrass P function satisfies a certain nonlinear ordinary differential equation, namely the derivative of the P function squared is equal to a cubic polynomial in P. And these coefficients, well, the first coefficient here is 4, then for the square term, there's no coefficient, it's 0. And then we have coefficients that are traditionally called G2 and G3. You can explicitly somehow express these coefficients in terms of the given lattice. There's certain Eisenstein series. Let me not write this down. So what will be more important for us is that you can always factor this cubic polynomial in linear factors with 3 distinct roots, and they're traditionally called E1, E2, E3. Right. As you see from the equation, this exactly corresponds to the, I mean, these e's correspond to the critical values of the P function, right? Because if P is equal to one of these e's, then the derivative of the P function has to be 0. And we know exactly where these zeros are relative to the lattice, namely they're exactly at the half period points, accepting the lattice points themselves. And it's very important to somehow find a consistent way to label these e's. So here's my convention. So omega 1/2 gives me E1, omega 2 gives me omega 2/2 gives me E2. 3 is what you get if you add these omegas together and divide by 2, right? And since the so as I said, they're all distinct, and the sum is equal to 0, which is just the fact that the p-squared coefficient here vanishes. Okay. Well, I need one more function that was introduced by Weierstrass. This is a little less well known, and it's about zeta function. That's what zeta function. For the zeta function, instead of having a second order poles, we'll have first order poles. The expression is a little longer, right? And again, I mean, the lattice here is understood, but sometimes we have to remember the lattice or the lattice generator. So let me not write this. This is 1 over z plus a similar sum for all the non-zero lattice elements. Again, I mean, the main term here is a term that gives you a pole of order 1. But now you need extra terms to make sure that this series converges. And in contrast to the P function, you actually need 2 terms. Okay, so this is a meromorphic function in the plane with first order poles exactly at the lattice points. And there's a simple relation between the zeta function, P function, namely if you differentiate this expression, which you can do term by term, then you get the P function up to psi. Follows from some basic facts about elliptic functions that the zeta function cannot possibly be a doubly periodic function. If you add these omegas to the argument z, you cannot expect that the zeta function remains unchanged. But you get, in some sense, the second best thing after that, namely the zeta function has a quasi-periodicity property. And if you add one of these omegas here to the argument, then some constant pops out. Right, and these constants are traditionally called the so-called quasi-periods. As I said, I mean, not both etas can vanish, right? Because the zeta function cannot possibly be a doubly periodic function by the so-called Liouville theorems. And this is reflected in the so-called Legendre relation. So the omegas and the etas satisfy some kind of a determinant type equation. So if you look at this expression, then it's actually equal to 2 pi I. Right, that's the Legendre relation. All right, so one last thing here that I need to get back to these funny constants. Namely, I somehow I have to get my hands on my eta here explicitly on my etas. And well, there is a standard formula for this eta 2, let's say. I mean, once you know eta 2 and the omegas, you can easily compute eta 1 from the Legendre relation. You can compute it in terms of information that just has to do with the lattice. There's a certain function that appears here. This is traditionally called E2. Tau tau here is again the ratio of the lattice generators. And what is this E2? Yeah, remember, tau was this ratio, Q was e to the I tau. This E2 of tau, well, is what is called, yeah, it's almost a modular form. Not quite, it's a so-called quasi-modular form. Let me write it like this. That's some other way to represent it. So if you know anything about modular forms, then you know that they should have a nice invariance property or nice covariance properties under the modular group. One thing is immediately clear. This is a one periodic function, right? Sorry, a one periodic function, right? Because my Q here, remember, this was e to the I tau, but we only see Q squared here in the expression, so this actually will imply that it's variant under shifting by 1. And then there is something that resembles what you would expect from a modular form. And if you feed in a generator of the modular group, then you get a factor tau squared. Right, so if it was like this, then you would have what is called the modular form of weight 2, but there's an extra term. This makes this expression quasi-modular. This is a quasi-modular form. Now let's try to relate all of this.
The denominator? 6i over
In n q to the 2n and 1 minus q
to the bottom 6. It's 6 still n. 6i over.
Yeah, here. Yeah, it's 6i over pi. Yeah, so let's get back here to this business, right? Somehow, of course, I mean, we would like to translate all this equation. Remember what it was: 2e kappa minus capital K of kappa equal to 0. We would like to express this somehow in the Weierstrass formalism. Right? In some senses, it's straightforward if you have some other right point of view. And well, we use some standard relation, I mean, that everybody in this area knows, how to somehow relate the kappa and the tau, right? So, it's my way. What the kappa and the tau somehow have to do? Well, we saw earlier, it's still on the board, that if you know the kappa, then you can pass to the tau, but it also works the other way around. The standard formula is this. So kappa squared is equal to, well, what is usually called lambda. This lambda actually can be expressed in terms of the e's. The E3 minus E1, E2 minus E1. This is the so-called cross ratio. Right. And well, I mean, we know that these guys here it just depend on the lattice. So they're functions of my two lattice generators. They will actually be, I mean, as you see from these formulas, homogeneous of degree -2. So if you take a ratio, you get a function that is homogeneous of degree 0. That means it just depends on the ratio of the omegas. In other words, it's a function of tau. Right? So this means actually we can consider these kappas and the lambdas here as functions of tau. And you've all seen what this function lambda of tau actually does geometrically. Namely, this is just a conformal map of, well, the famous modular triangle with angle 0 from the tau plane to the upper lambda half plane. Right, so this is what my lambda does. So that actually there's a certain correspondence between 0 and infinity. With the normalizations, I have actually infinity goes to 0. 0 goes to 1, and 1 will go to infinity. Right? So in other words, if you run along the boundary like this, then your modular triangle is to the left, and well, this is the reason why you get the upper half plane. Okay, so once you have this relation between the kappa and my tau, I can somehow revert the whole thing, right? So now kappa can be considered as a function of tau. So my elliptic integrals here will be functions of tau. I can try to express everything in terms of these Weierstrass functions. And this is indeed possible and a fairly straightforward and in some sense well-known computation. Let me just write down the result here as a lemma. Proof. Two E of kappa. Kappa now considered as a function of tau minus this A of kappa. Again, kappa considered as a function of tau is equal to 1 over root E2 minus E1. Some other expression, but let me make a quick comment here about this expression, right? The E's are distinct, so this means the difference of the E's never vanishes on the on my domain of definition, the upper tau half plane. So this means at least this expression is non-zero. I have to be a bit careful how to choose the root, but there's a consistent choice of the root, so that actually this makes sense. And the whole expression then can be written in terms of my eta. This E, one of the E's, it's actually E3 and omega 2. Let me call this expression f of tau. Okay. So if we are interested in roots of this expression, well, then it boils down to studying this function as a function of tau and trying to find the root. So let me write this down as a general problem. Investigate zeros of f in the upper half plane. Right. So I think I convinced you that it's very easy to see that my equation here has actually a tau, a kappa in the interval 0, 1 that makes this expression 0. This just corresponds to the fact that my expression here as a function of tau will have a 0 on the positive imaginary axis, right? Because the positive imaginary axis under my lambda or kappa is actually mapped to the interval 0, 1.
So you're saying basically that this is kind of a, if you're fluent in the language of elliptic functions,
This is totally straightforward.
This is kind of straightforward.
You can even put this together from some classical books. I mean, for example, Fricke's book on elliptic functions, he even has explicit formulas of this E and K in terms of these expressions. And you can just put this together, you get this, but it's not hard to prove this actually from scratch. Okay, so there's really nothing mysterious here. This is all, I would say, fairly standard. But the question that I want to get to it now is, all right, I mean, we have this kind of modular function or something. It's a function on the upper half plane, right? We have seen that the 0 on the positive imaginary axis is somewhat interesting because it leads to all these kind of funny constants. right? So why don't we study this function and just to try to determine all zeros? Yeah, this is really what I want to do. I want to explain to you how you actually can look at this function in the right way, the geometric way. And you, if you do this, then you can actually kind of read off where the location of these zeros actually, where they are. Okay. Okay, let's see. So what can I erase? So let me.
From the tau coordinates, your kind of real kappa becomes purely imaginary.
No. Where's my formula? Here. So if tau lies on the positive imaginary axis, then lambda maps it actually to the interval 0, 1, right? Because the axis corresponds to 0, 1. So lambda is there. Well, then it's not hard to believe that with the right choice of the root, kappa will be there, right? So tau, the form IIT positive corresponds actually to kappa. This is what I'm saying. I mean, from this elementary argument that looking at the graphs of these functions as functions of kappa, you can immediately see that in the tau plane there will be a root somewhere here. But natural question is, are there other roots? How can we get our hands on all the roots? And do these other roots also have some interesting properties, right, corresponding to the properties of this constant that we have seen? So how do you study such a question? Well, this relates to some previous work of mine, where I looked at something very similar for, well, a simpler function. Namely, the function that I looked at was actually this eta 2. Yeah. So, well, finding the roots of this eta 2 is equivalent to finding the roots here of this E2 function. This has been studied a lot in number theory. Actually, a colleague of mine, Bill Duke, says that this E2 is his favorite function. Right. So, I mean, if there's such a function, I mean, then you want to somehow try to understand the function. And well, I mean, finding the roots of a holomorphic. So how do you approach this question? And in my paper, so this is a paper called the quality periods of the Weierstrass zeta function. You can find it on archive on my website. It's currently being in press. I use the following approach. Namely, instead of looking at this eta just by itself, I introduced a function, namely the ratio of these etas. Okay. And again, I mean, these etas actually are homogeneous of degree -1. So if I take a ratio, then I can consider this as a function of tau alone. And this now is a meromorphic function. And finding the roots of eta 2 of E2 is equivalent to finding the poles of this function. And actually proved in my paper that this function P, this ratio of the etas, has a very simple mapping behavior. Namely, it maps this triangle. I mean, this now is essentially a fundamental domain of the full modular group. It maps this triangle to the triangle that I get if I somehow extend it to the lower half plane. Right? It was somehow very easy to describe the geometry of this map. Once you know the geometry of this map, I mean, you can read off what the poles are more or less. Okay, so this suggests that for our problem here, we should try a similar approach. And indeed, this approach actually works and leads to interesting results. What do I have? 20 minutes, 10 minutes, 20 minutes. So this is what I will try to explain the rest of my talk. So let's try to do a similar thing here, right? I have this expression. And if we want to do something like this here, then it's somehow clear what we should do. Namely, let's just change this index 2 here to 1 and take the ratio of these two things. And then we get a function that I call R of tau. So this is just the ratio. Yeah, this then cancels. Just have eta 1 minus 1/2 eta 3 omega 1 divided by eta 2 minus 1/2 E3 eta 2. Okay. So the poles of this function correspond somehow to the zeros of this function. With this expression is in the denominator. It's not hard to see based on the Legendre relation that these two expressions cannot vanish simultaneously, right? So as a value in the Riemann sphere, this is well defined. So it's a meromorphic function on the upper half plane, and we want to understand what this function is. Okay. So one can actually write this function quite explicitly again in terms of my E. This will not be super important for the rest of my talk, but let me just use this here as a little side remark. So I can express my meromorphic function R in the following way. Right. So you see that the poles actually correspond to the zero of this difference. And Alex, if you're still awake, here's an exercise for you. Show that this denominator, right? We're interested in where this denominator vanishes. Is equal to 3 minus 24. Right, remember this E2 was somehow defined in terms of this Q series. So we expect a very similar thing. The Q series that you get in this case looks like this. It has exactly these coefficients that we have seen earlier today. D divides N minus 1 to the D. E, well, I wrote X, now it's actually So this somehow explains, I think this was the first equation that I wrote for this X naught, right? This somehow explains why actually this Euler problem has something to do with this Rachmaninoff problem, right? I mean, it's an easy manipulation, but just kind of slightly not trivial. I mean, you have to keep a little head and order the terms in the right way, but yeah. This is.
So what caused that 1/8 in the original equation?
Well, I mean, if you throw this to the other, 3 divided by 24 is 1/8. Okay. Okay, so this explains some of these analytic facts, but I wanna get to a more geometric approach, which is more fun. Right, so remember, I mean, we now want to study some of this function, and there's another small reduction that one can make, which I will not explain in detail. For the experts here, this has to do with division of elliptic functions by 2. So if you apply some standard formulas, then you can actually show that this function R that I wrote here is related to a function that I call S, namely it's 2S tau plus 1 divided by 2. And what is this S function? S now is this expression that is very similar to this expression. It's again, I see these etas, I see some E, now it's E2. Oops, omega 1, eta 2 plus E2 omega 2. Okay, so as I said, I mean, this follows from some kind of standard manipulation and computation with the so-called duplication or division formula for elliptic function. This, by the way, is related to elliptic integrals, namely the numerators here. They are periods of a certain elliptic integral. This was actually an integral that Alex at some point investigated. And he asked me whether, you know, these integrals here satisfy a hypergeometric equation, and it actually turns out they do. And this is more or less at the basis of the main theorem that I want to formulate. So theorem S, this map here is a conformal map. And, you know, I can exactly say what it does, and I just do this by a picture. Well, conformal map on the fundamental domain of the, well, a modular group in the upper half plane. So I will just show you what it does on one of these modular triangles, right? And then you can extend it by reflection to the whole upper half plane. And it turns out that the map is actually something very simple. Namely, it maps the modular triangle to something that actually is bounded by arcs on the same circle as the original triangle, but you somehow reflect this below. One of the two of the arcs are fixed, and the other arc is just reflected below, and the image then is everything that you get here. So what this means is that you have here three angles 0, but in the image you will have one angle 0 and two angles pi. But the nice thing about this is that if you do any kind of reflection, right, these are arcs on the exact same circles, right? And this means that my S here will have some kind of polymorphic property. Namely, if you feed in any of these reflections, then actually I get commuting behavior. And so, for example, if I reflect here in the positive imaginary axis, then the image will be reflected in the positive imaginary axis in the same way for the other arcs. And this actually allows you to get a very good intuition what the geometry of this map does. And let me use this picture now to explain to you why my R function, the original function that I'm interested in, why it actually has a 0 on the positive imaginary axis. You see it actually from this picture. Let me try to explain this.
So what is A?
A is the positive imaginary axis. So A, B, C are the sides of my modular triangle. A, B, C. And well, I mean the sides or the reflection generated in the side. Right. And what I'm saying is if you do reflection in any of these sides, the image undergoes exactly the same transformation. It has some kind of equivariance property with respect to the group generated by the reflections in these sides. Let me try to convince you why this explains why my function R here has the root on the positive imaginary axis. And in order to do this, let's reflect the modular triangle here in this side B. Okay, so what do I see if I do this? Well, I mean, these points here will stay fixed, and the point infinity will actually reflect to the center of this circle, which is at a half, right? So the picture that I will get is something like this. All right, so this is the image. So let me give a name here. So let me call this T. So what I'm drawing here is, well, B of T, where we somehow inflate notation for sides and the reflections that they generate, right? So this is B of T. But now what happens if I map with S, right? So I reflect it in this circular arc of B. Well, so I should reflect also here in this circular arc, let me call it B tilde, right? That bounds my image here, right? But this is reflection in the same circle. What actually happens under my map is that two sides are somehow preserved, right? As in this picture, two sides are preserved. And then there's one active side that is somehow mapped to the complement, right? And in this picture, actually, this will be the active side. And these circles here, these semicircles will be preserved under the map. No, if my image somehow will be bounded by, again, these two circles. But then something else. And how do I get this something else? Right here, I had to take my circle and somehow take the complement of of the circle and fill the whole disk. So let's do a similar thing here. So I would have to take the complement of this circle, the active of this, and reflect and fill, right? What this means is actually what I will get in the image is with the well, so this means that if I run along this line 1/2 plus IT, right, then here we'll run through infinity coming back here. Right. So this means there has to be some pole here somewhere here. Does that make any sense? Right. So the
What are the pies in your picture? Sorry, in the right.
pi.
On the right-hand side.
The right-hand side, it's here.
The right-hand side of that picture.
The angles.
This one.
Ah,
Right. So you have angle 0, you
okay.
have angle pi. Right. So let me repeat. I mean, if you play with the reflection symmetry that you have here, then you see that under S, this triangle is mapped to the complement of this kind of heart-shaped thing. Almost the whole plane, the Riemann sphere, with the exception of incomplex set. In particular, if you run along this line segment from 1/2 to 1/2 plus I/2, right, then the image will actually trace out everything here from 1/2 up to this point, and in particular, there will be a point where actually I have a pole. Right. So S has a pole. So let me write this. S has exactly one pole on this line on rays. Right. I mean, why is it exactly one pole? Well, I mean, my map is a conformal map. But here in this picture, you know, I certainly don't get poles. Right. I mean, in the open upper half plane. Well, infinity is a different. Well, but look, I mean, let's look at this formula here that relates my R to S, right? So if I feed in something from the positive imaginary axis, then I exactly run on this ray that I have over there. So this is actually equivalent with saying that R is exactly pole like a T positive. But actually, by this kind of geometry, you can determine, or you can somehow see all poles of the map S and hence of the map R. Essentially, what happens is that these modular triangles, they come in pairs, right? And they're separated by some kind of an active site. And under the map, the non-active sites are preserved, but then the active sites somehow create a large image, which always gives you a pole, right? So I can actually pair these modular triangles up so that in each of these pairs I have exactly one pole, right? So in particular, I have infinitely many poles of S and hence of R. And it's not too hard to say to see that they're actually all inequivalent, so they're not equivalent under the modular group. Okay, so my time is almost up. So let me say in the remaining few minutes here something about the proof of my theorem. Okay. This is one of these proofs. In the near future, the proofs will be given by AI. Because the strategy of the proof requires no thinking or intelligence. Some are very straightforward. The idea of proof. Here are my fingers here. The strategy for proof of theorem. Well, I mean, I maybe missed saying this, but my map S here actually preserves these vertices 0, 1, infinity. Okay, so show that S preserves 0, 1, infinity, fixes 0, 1, infinity. This is not totally trivial, but for this you somehow need this explicit expression that I wrote down here for my R in terms of this E2, right? So I would say this is a rather easy step. Work with some asymptotic expansions that you get from these Q-series expansions. And the other step is, well, you want to show that something is a triangle map, right? So how do we show that something is a triangle map? We compute its Schwarzian derivative, right? And then verify that the Schwarzian derivative corresponds to the Schwarzian derivative of a triangle map. There's a small complication here. Namely, we want to show that a triangle maps to another triangle. And if you know anything about Schwarz triangle maps, then usually you map a triangle to the upper half plane or something like this, right? So it seems very natural to bring in here an auxiliary map that maps to the upper half plane. Well, we know a map that maps this modular triangle to the upper half plane, namely our elliptic modular function lambda, right? So it's somehow natural to bring in this lambda and then show that under this map, under S, if I go in this direction, my upper half plane is mapped to this triangle, which I then can compute from the Schwarzian derivative. Right, so in other words, what we really want to do is compute Schwarzian derivative of my function S, but not as a function of tau, but as a function of lambda. Okay? And you will agree, I mean, it's just a computation, how hard can it be? But if you actually want to implement this computation, I mean, then you run into very, very serious problems. Actually, with a student of mine, Zach Smith, we implemented this in Sage. Sage kind of collapsed. It couldn't do it. It spit out some pages and pages of computation. And not for this problem, but for a related problem, because it somehow didn't cancel the terms properly. After some massaging, actually, we were able to do it. But what I'm trying to emphasize here is that this is not really as it sounds, right? How do you even start? Right? How do you get your hands on these derivatives? And well, you use a secret weapon that seems to have been forgotten. So it's from the classical literature. I think it goes down all the way back to Weierstrass, actually, namely a certain differentiation process of homogeneous modular forms. Right nowadays, everybody just looks at homogeneous, inhomogeneous modular forms. But actually, the secret here is to facilitate these computations, to look at these modular forms as a function of two variables, right? I mean, I try to convince you that it's always good to look at the function of these functions of tau, but for these computations, it's actually better to again look at these as functions of omega 1 and omega 2. So use these differentiation process, and then, you know, one of the nice things, let me just write down a random. For example, if you hit the e's that are involved here in the definition with this differentiation process, then you can write this in terms of polynomials in E. So for example, if you apply this differentiation process to E3, then actually get a polynomial in the other. These are again classical formulas that are recorded, for example, in Fricke's book. There's similar formulas for the other terms here. So for example, this differentiation process applied to the elliptic modular function lambda gives you 2 times E2 minus E3 times lambda. Right? And once you have this, I mean, then you can easily compute lambda derivatives of functions in terms of this eta process, essentially by the chain rule. Right? So for example, I mean, the first lambda derivative is just the ratio of the eta process applied to the functions. But here you already see what the difficulties could be. Right? I mean, these differentiation processes are like a hydra. So if you apply the process once, I mean, 2 new arms emerge, right? But for the Schwarzian, you have to compute the third derivative, right? So you get terms and terms and terms. But fortunately, somehow at the end of the day, they somehow all cancel. You get a pretty nice expression for the Schwarzian from which you can then read off. I mean, that, my upper half plane has to be mapped to a circular arc triangle with angles 0, pi, pi. And since we know what the vertices are by the first step, we can identify what the triangle actually is. And then this shows that we get the map S as in the figure. Okay, so let me stop here. And again, happy birthday, Alex. So I wanted to get this paper finished, for your conference, but I didn't quite succeed.